Uniform ring of charge. A positive charge Q is uniformly distributed on a ring of radius r centered on the x-axis and in the yz plane. So here's our x-axis down here, here's y, here's z. Find the electric potential at a point P, a distance a, on the x-axis. Right there. Where along the x-axis is the electric potential maximum? Find the x component of the electric field at point P, and what are the y and z components of the electric field at point P. Then, find the distance on the x-axis for where the electric field is a maximum, find the maximum value of the electric field, and on the axes here, sketch the x component of the electric field as a function of x. Find the electric potential at point P, which is a distance a from the center of the ring. We use our equation for calculating voltage due to a continuous charge distribution, and we're taking a little dq up here to start with, and we find that the distance r, which will be the distance from any single point on this ring, is going to be the square root of capital R squared plus a squared, just using Pythagoras. We insert that into the equation, we remove all the constants, and then we're integrating a little dq. That means you're adding up all the little bits of charge going around the ring, and that's just going to sum to Q. So here's our potential at point P. Where along the x-axis is the electric potential a maximum? We examine the electric potential equation, and we find that Q is a constant, R is a constant, that's the radius of the loop, these are constants, so the only thing we can vary is A, the distance from the center of the loop. We want to maximize the electric potential, which means we need to minimize the denominator. So to minimize the denominator, we set A equal to 0. So when A is equal to 0, the electric potential along the x-axis is a minimum. And where is that going to be? Right here, right at the center of the loop. Find the x component for the electric field at point P. We first have to take our voltage equation here, where we have a fixed point A, and replace A with x, because we need to take the derivative of the potential with respect to x. So we substitute in x, and we have this, and then we know that the electric field in the x direction is minus dV dx. So here's our minus d by dx, and here's our expression for the potential, where we're expressing the square root in the denominator as the argument to a negative power in the numerator. That will make it easier to take the derivative. This is from the previous slide. Then we will use the chain rule to take the derivative. The negative 1/2 comes out in front, times the value inside the parentheses, and you subtract 1 from negative 1/2 and get negative 3/2. Then take the derivative inside, you get 2x. Simplify, and here it is in terms of any x, but we're looking for the value at point P, so we substitute A back in, and we get the electric field is qx divided by 4 pi epsilon 0, r squared plus a squared to the 3/2. What are the y and z components of the electric field at point P? Well, they're both 0 due to the symmetry of the disk in the y and z plane. And at this point here, let's just take this and this, these two charges, bits of charge. This will have an electric field up like this. This will have like this. So along the y-axis, you can see that they'll cancel out. And similarly, you can do that along the z-axis. Find the distance on the x-axis for which the electric field is a maximum. To find a maximum, you take the derivative of the function, in this case the electric field, and set it equal to 0. That will find a critical point. To check if it is a maximum or minimum, either take the second derivative, which is going to be messy, or find the value of the electric field on either side of the critical point. Let's start by taking the derivative of the electric field and set that equal to 0. You factor out the constants, then we have d by dx of x times parentheses r squared plus x squared raised to the negative 3/2. We're going to use the chain rule and the product rule to evaluate that derivative. But first thing we'll do, we'll divide both sides of the equation by the constant. And since we have 0 over here, that just goes away. So what are we doing first? We take the derivative of x and hold the rest of the expression constant. And then we keep x constant and take the derivative of this expression. So that's going to be negative 3/2 times r squared plus x squared to the minus 5/2. Then you need to take the derivative of what's inside the parentheses, and that's where this 2x comes from. Find the distance on the x-axis for which the electric field is a maximum. We start with the equation from the last slide, right there, and then we just do a bit of algebra, right? This 2 cancels out this 2, and then we move this entire expression over to the right side. Then we divide through by this one over to here, and we get r squared plus x squared equals 3x squared. And finally, we get x is equal to 0.707 times r, the radius of the loop. For the purposes of AP exam questions, you won't have time to take the second derivative. So just assume if a maximum was asked for, that's what was found. Or, better yet, if you have time, use the argument starting on the next slide. While the reasoning on the previous slide was pragmatic, it's not very satisfying. So let's consider the physics of the situation by examining values of the electric field between the center of the ring, where x is equal to 0, and x is equal to infinity. And here's the point of interest, 0.707 times r. The electric field at x equals 0, right here, is 0 because of the ring symmetry. Every contribution to the field by a segment of charge on one side of the ring is canceled out by its counterpart on the other side. So let's sketch a quick picture. Here we're looking at the loop edge on. So this, we have a positive ring. Let's take 2 points on either side. This one will have an electric field going this way, this that way. They're the same distance from the center, so they cancel out. So as we draw this, here's our x-axis. We know we're 0 right here. And we found a critical point at this point, 0.707 r. We know the electric field starts going up as we go away from the loop. Now, at infinity, the electric field is 0. And here's where we found the critical point. So if we start going up here to get to this point at 0, somewhere we have to hit a maximum and then start going down again. So we will assume that this point here does give us a maximum electric field, and we don't have to go ahead and take the second derivative. To find the maximum value of the electric field, we substitute in x is equal to r over square root of 2 into our expression for the electric field. So that's done here, here, and we come up with this answer. So please work that on your own and verify the algebra that I did. And if it's not correct, please send us an email. On the axes, sketch the x component of the electric field as a function of x. Now, what does the word sketch mean? Well, from the AP Physics C College Board website, they tell us that sketch, and this is a quote, means to draw a graph that illustrates key trends in a particular relationship, such as slope, curvature, intercepts, or asymptotes. Numerical scaling or specific data points are not required in a sketch. On the axes, sketch the x component of the electric field as a function of x. Well, first, just to give us a sense of what's going on, I use graphfree.com and I graphed this expression. You might say, where did these numbers come from, this 0.7? Well, trial and error, all right, because this value could be almost anything. So I just wanted to put some numbers in to get a nice idea of the shape, and here we go. On the AP exam, you could use a graphing calculator. But can you do it without this device? And also, you may be asking, why is the electric field negative down here? Well, that's just a function of the math, okay? Because we know the electric field will be positive on either side of the loop. It's a positive charge. But check this out here. X, on this side of the y-axis, x is negative. So if I put a negative value in for x, that will give me an electric field that is down here. So in reality, the electric field is positive, but this guy here makes it look mathematically as if it's negative. Yes, you can sketch this. For example, at x equals 0, you know that the electric field will be 0. So that's this point here. For large x, as x goes to infinity, that'll dominate this r squared. X squared will be much greater than r squared. You'll have x over x squared, that's 1 over x. You'll go to 0 there also. So those are the 2 points there. You know you have a maximum at 0.707 r, so you draw in maximum, and we're just going to worry about the right side for a second. Then for small values of x, x will dominate this x squared term, so it'll look fairly linear. So that's the shape here. You kind of go up in a linear fashion, and then once you get past the maximum, this x squared will start dominating, and you'll have, this goes away, so it'll be 1 over x, so it'll fall off as 1 over x. And then you just flip it to the other side. On the previous slide, we had this, right? It went up, and mathematically it graphed as this. But you know that the electric field will be positive on both sides, so we'll overrule the math diagram here and draw E positive. We'll mirror the image for the negative x-axis.